Good morning, all of you. Welcome to see J in the rank zone. So, in the previous session, we have discussed 15th group and 16th group elements. Now, in this session, we are going to discuss 17th group and 18th group elements of P block elements. So, listen carefully. So, this is very easy chapter. Only memory based questions you will get from this chapter, from these two chapters for competitive exams. So, now we are going to start. We are going to start now. P block elements, 17th group and 18th group. So, listen carefully. So, in 17th group elements, what are 17th group elements? These are also called as halogens. So, what are the halogens we have? Fluorine, chlorine, bromine, iodine, and astatine. Fluorine, chlorine, bromine, and iodine, and astatine. These are the elements of 17th group elements and 18th group. So, 18th group also we are discussing now. So, first we'll finish up 17th group, then we'll go for 18th group elements. I hope it is clear. Let us start the new topic, that is 17th group elements. So what are 17th group elements? Like how we have studied for 15th and 16th group, we also will study about 17th group. 18th group is different from all the other groups and it is coming under P block elements. So let us start now. Fluorine, chlorine, bromine, iodine and astatine are 17th group elements. Out of this, astatine is radioactive, so we will not study about this compound because it is radioactive. So radioactive element means it undergoes alpha, beta and gamma radiations. So that's why this element will not be studied under this. Only we will study about fluorine, chlorine, bromine and iodine. These groups are commonly called as halogens because seawater contains halogens. That's why it is called in Greek word halo means seawater. So these are present in seawater as salt producers. That's why these are called as halogens. Halogens means in Greek word halo means seawater. As these elements are present in the form of their respective salts, so that's why these are called as halogens. I hope it is clear. So let us see next one. So fluorine, chlorine, bromine, iodine, and astatine. So the symbol of fluorine is F, Br, so Cl, chlorine is Cl, and bromine is Br, iodine is I, and astatine is AS. 80, sorry, it is 80, astatine. So these are the symbols of the elements. Let us see now what are the trends of properties in these elements. Occurrence. Fluorine and chlorine are rarely abundant in nature. These are present in nature. Fluorine is present mainly as insoluble fluids like calcium phosphate, calcium fluoride, fluorapatite. It's a mineral from where we can extract calcium. Fluorspar, from this also we'll extract calcium. It is CaF2. And cryolite, Na3AlF6. This cryolite is very, very useful compound. This cryolite we'll use in the extraction of aluminium from alumina. So this is called cryolite, formula is Na3AlF6. Seawater contains chlorides, bromides, and iodides, 2.5% by mass of sodium chloride. So since all these elements are present in seawater as their salts, so that's why these are called halogens. Deep sea weed ashes contain 0.5% iodine in the form of iodic acid, that is iodate. This is called iodate ion. Chili salt petri is sodium nitrate, which contains traces of sodium iodate. Sodium iodate. So NaIO3 is called what? It is called sodium iodate. Sodium iodate. IO3. So these are the salts. These are the occurrence of these elements. So these are fairly abundant in nature. Fluorine is present mainly as insoluble fluids. I hope it is clear. Let us see next. General trends. As we have studied in Go 15 and 16, we first will study about general physical properties, then we'll study about general chemical properties. So general chemical properties and general physical properties. So first we'll discuss about physical properties, that is electronic configuration, atomic and ionic radii, ionization enthalpy, electronegativity, and electron gain enthalpy. So let us see now. So the outermost electronic configuration of halogens is Ns2np5. Since they have seven electrons in the valence shell, since they have seven electrons in the valence shell, that's why they are also placed in seventh A group elements. These are 17th group element is also called as seventh A group elements. Seventh A group elements, as they have seven electrons in the valence shell. So that is the configuration is Ns2np5. For fluorine, it is 2s to 2p5. Chlorine, it is 3s to 3p5. Bromine, it is 4s to 4p5. 5s to 5p5 for iodine. And astatine, 80, it is 6s to 6p5. I hope it is clear. So this is the electron general outermost electron configuration of halogen atoms. And out of this, fluorine is the most highest electronegativity element. That's why its oxygen state is always -1. Highest electronegativity is fluorine. Electronegativity is flowing. Its value is around 4.0 based on Pauling scale. So electronegativity value of fluorine is 4.0 based on Pauling scale, and is highest electronegative element, and it exists as a diatomic molecule, that is fluorine F2 molecule. And most important point is the oxidation state. The oxidation state of fluorine is always -1. Next is chlorine. Chlorine is highest electron affinity. It has highest electron affinity of all the elements. Electron gain enthalpy or electron affinity. Electron affinity or electron gain enthalpy are same. So chlorine is having highest electron affinity, and it is electronegative in nature, but it is having highest electron affinity. And bromine is the only liquid nonmetal. Only liquid nonmetal is bromine. Liquid nonmetal. Iodine exists as solid and iodine molecule. So iodine vapors, iodine solid changes to iodine vapors. So that is nothing but iodine. And bromine also exists as diatomic molecule. Chlorine also exists as diatomic molecule. And astatine is radioactive, so we'll not study about this. So this is a radioactive element in nature. So the radioactive element in 17 group is astatine. Its atomic number is 85. So above 80, all are radioactive. So they undergo alpha, beta, gamma radiations when exposed to light. So that's why these radioactive elements will study in nuclear chemistry. I hope it is clear. So the general electron configuration and the important points I have discussed. So please note down in your classwork. The highest electronegativity element in the periodic table is fluorine. That's why it's always negative. The oxygen state of fluorine is exhibiting only -1 only. In any compound, it exhibits -1. In free state, it is 0. Already you know that. Next, the highest electron affinity is the most electron gain enthalpy element in the periodic table is chlorine, and bromine is liquid nonmetal. All these are nonmetals only. All the elements of this group are non-metals. They combine with metals to form metallic chlorides, etc. So metal halides. So these are called non-metals. All these are non-metals and mostly electronegative. And astatine is radioactive non-metal. I hope it is clear. Next, atomic and ionic radius. The atomic and ionic radii increases from fluorine to iodine due to increasing number of shells. As the atomic number increases, automatically atomic radius and ionic radius also increases. So what is atomic radii and what is ionic radii, we already know. These halogens have the smallest atomic radii in their respective periods due to maximum effective nuclear charge. As they're having effective nuclear charge, because due to post-shielding effect, they have effective nuclear charge, and due to which what happens, they have smallest atomic radii in their respective periods. Periods means from left to right, if you take into consideration. So across the period, always across the period, what happens? The atomic radii decreases. Atomic radii decreases across a period. Down the group it increases, but across the period, that is from left to right, across the period, any period you take from second period to seventh period. So atomic radii decreases across period due to effective nuclear charge, because the same more number of electrons are added in the same subshell. So effective nuclear charge due to effective nuclear charge. So that's why in second period we have fluorine, third period we have chlorine, and so on. So the atomic radius across a period decreases. I hope it is clear. Next, ionization enthalpy. Ionization enthalpy decreases down the group because the atomic number increases. So the valence electron will be far away from the nucleus. So automatically ionization enthalpy decreases down the group. They have very high ionization enthalpy since they have little tendency to lose electrons. Since they are electronegative, so they want electrons. That's why they have very high ionization enthalpy within the period. So across a period, what happens? Across a period, ionization enthalpy increases. Ionization enthalpy increases. So this is about ionization enthalpy, variation of ionization enthalpy. Next, electronegativity. The electronegativity decreases down the group because fluorine is having highest electronegative value. As I told you, it is 4.0, chlorine is 3, bromine is 2.8, and iodine is 2.5 based on Pauling scale values. So the electronegativity decreases down the group. They have very high electronegativity values when compared to other elements in the periodic table. Fluorine is the most electronegative element in the periodic table, as we already know. I hope it is clear. So the electronegativity decreases down the group from fluorine to iodine. Next, electron gain enthalpy. Halogens have highest electron gain enthalpy in their respective periods. Halogens easily accept an electron to attain noble gas configuration because they are having one electron short. One electron short for attaining noble gas configuration, for attaining noble gas configuration. So that's why they always want electron to gain so that to become stability, for becoming stable. So that's why to attain stability, they always want of electron. That's why they have highest electron gain enthalpy in their respective periods. Among halogens, halogens easily accept an electron to attain the noble gas configuration. Fluorine has less electron gain enthalpy than chlorine. This reason is very important due to its small size and inter-electronic repulsion. Due to its small size and inter-electronic repulsion, fluorine, sorry, fluorine has less electron gain enthalpy than chlorine. I hope it is clear. So why chlorine is having more electron gain enthalpy? So electron gain enthalpy order, if you take into consideration, chlorine, then fluorine, then bromine, then iodine. This is the electron gain enthalpy order. Electron gain enthalpy order, or electron affinity order. I hope it is clear. Next, physical properties. All halogens are diatomic gases and astatine is radioactive, as I already told you. So all halogens, fluorine, chlorine, bromine, iodine, they exist as diatomic gases. All are gases at room temperature. Fluorine, chlorine, bromine, and iodine. Iodine exists as solid also. Their melting points and boiling points steadily increase with the increase in atomic number. So fluorine, melting point order, fluorine is less than bromine, sorry, chlorine. Fluorine is less than chlorine. Chlorine is less than bromine. Bromine is less than iodine. So highest is having iodine. Halogens are colored due to absorption of radiations in visible region. F2 is yellow colored gas. Chlorine is greenish yellow gas. Bromine is red color liquid. Iodine is violet solid. So as I told you, iodine is solid at room temperature. So all the halogens, these are the existence of physical properties of halogens. The melting points and boiling points steadily increase with the increase in atomic number. So this is the melting point and boiling point order, increasing order, decreasing order, reverse. Next, bond dissociation enthalpy is very, very important because they'll ask this exam in the examination. So many times they have asked this question in entrance exams. The bond dissociation energy decreases down the group due to increasing the size, and highest bond enthalpy is chlorine gas, then bromine, then fluorine, then iodine. This order is very, very important. So please note it down. The bond dissociation enthalpy or the bond dissociation energy or bond enthalpy decreases down the group due to increasing the size, but they are not from regular pattern. They'll form first chlorine, then bromine, then fluorine, then iodine. The low bond enthalpy of fluorine is due to strong lone pair repulsions. In fluorine, we have lone pair repulsions due to which it has lowest bond enthalpy. And the highest bond enthalpy of chlorine is due to the empty d orbital. Empty d orbital. So I hope it's clear. Not only this, one more reason is also there. So this order is very, very important. So please note it down in your classwork. Definitely they'll ask in examination. So the bond dissociation enthalpy order of halogens is as follows. Chlorine greater than bromine, greater than fluorine, greater than iodine. The oxidizing nature decreases down the group. Fluorine is most oxidizing because it can give it can bring oxidation so to others and itself undergoing reduction. So chlorine next bromine next iodine. Fluorine is the strongest oxidizing agent due to lowest. This reasoning is very very important. Low enthalpy of dissociation of fluorine bond. High hydration enthalpy of fluorine ion is high standard reduction potential in aqueous solution. So that's why it is mostly strongest oxidizing agent. It can oxidize chlorine, bromine, iodine. Chlorine can oxidize bromine and iodine, and bromine can oxidize only iodine, and iodine cannot oxidize anything. So these reactions, fluorine can oxidize chlorine. So fluorine on reaction with 2 moles of chlorine, it forms 2F minus and Cl2 molecule. Chlorine on reaction with 2 moles of bromine and iodine, and it forms 2Cl minus and bromine is displaced. So fluorine can displace chlorine, bromine, and iodine. Chlorine can displace bromine and iodine, and bromine can displace only iodine. I hope it is clear. So this is the highest, its high standard reduction potential in aqueous solution. So fluorine is the strongest oxidizing agent among the following. I hope it is clear. Next, oxygen states of halogens. All halogens exhibit first, basically they exhibit -1 oxygen state because they require one electron for attaining stability. So that's why they will exhibit -1 oxidation state. Due to high electronegativity and absence of d orbitals, fluorine exhibits always -1 only. And chlorine, bromine, iodine can exhibit, apart from -1, they can exhibit -+1, +3, +5, +7 oxygen states along with -1. So chlorine +1, if we take into consideration CLF, so it is oxygen state is +1, fluorine is -1. And if we take chlorine, ClO2, ClO3, ClO3 minus, if you take like this, you will get. So chlorine can exist in oxygen states, that is +1, +3, +5, +7 due to availability of d electrons in all these chlorine, bromine, and iodine. Next, the positive oxygen states of halogens are found in interhalogen compounds. Interhalogen compounds means between two halogens a compound is formed, like IF7, interhalogen compound IF7. So oxygen state of iodine is +7. I hope it is clear. So this is called IF7. This is called interhalogen compounds. So more about interhalogen compounds we'll discuss in the meanwhile. So the positive oxygen states of halogens are found in interhalogen compounds, oxides and oxyacids. So for example, as I told you, HClO3. HClO3, chlorine exhibits positive oxygen state. Hydrogen is +1 and chlorine is +5 and oxygen is -2. So total it is +5. I hope it is clear. So even Cl2O7 2 minus, Cl2O7 also 2 minus, this is also Cl2O7 also we can take, this is +7 oxygen state, Cl2O7 is not 2 minus, so simply I write to Cl2O7 molecule. So oxyacid of chlorine, this is called what? Oxyacid of chlorine. I hope it is clear. So the positive oxygen states of halogens are found in interhalogen compounds, oxides, some oxides, and also some oxyacids. I hope it is clear. Next, continuation. Hydrides of group 17. So physical properties we have completed. Now we'll see chemical properties of group 17 elements. All halogens react with hydrogen to form HX type of hydride. All halogens react with hydrogen to form HX type of hydride because they combine with hydrogen because hydrogen is positive, electropositive. Halogen is electronegative. So they form halides of type HX. So these are called acids. Basically, these are acids, hydra acids. What we'll call them as? We'll call them as hydra acids. Hydra acids means so hydrogen fluoride, hydrogen chloride, hydrochloric acid, hydrogen bromide, and hydrogen iodide. So all these are nothing but hydra acids. So They combine directly with hydrogen. So fluorine combines with hydrogen in the dark and forms 2 moles of hydrogen fluoride. Chlorine combines with hydrogen only in the presence of sunlight and forms 2 moles of HCl. Hydrogen combines with bromine in the presence of sunlight at high temperature. It forms 2 moles of hydrogen bromide. And hydrogen combines with iodine in the presence of platinum as catalyst and presence of sunlight and platinum at 570 kelvins high temperature and forms hydrogen iodide. So stability is a formation of HX bond. Enthalpy decreases from HF to HI. So most stable is HF, next HBr, next HCl, next least stable is HI. So bromine is having more because so the bond dissociation enthalpy of hydrogen bromide is greater than hydrogen chloride. This is very, very important. So wherever you find the order not regular, if the order is not regular, that is fluorine, chlorine, bromine, iodine means regular. But here we are getting hydrogen fluoride, hydrogen bromide, hydrogen chloride, and hydrogen iodide. So that's why this is the order is different. So this type of orders are important for examination point of view. For entrance exams, they'll ask this type of orders only. So they'll ask the bond is a formation of HX bond enthalpy decreases from HF to HI. So which will form easily the hydrides, hydroacids, first fluorine, next bromine, next chlorine, next iodine. Next, hydrates of group 17, the acidic strength. The acidic strength and reducing property increases down the group. HF is less acidic when compared to HCl, then HBr, then HI. HI is the strongest acid. So, strong reducing agent down the group. So, HF has high boiling point and exists as liquid at room temperature due to intermolecular hydrogen bonding. In hydrogen fluid, we have what? Intermolecular hydrogen bonding. Apart from HF, we do not have intermolecular hydrogen bonding in any of these cases. Only with HF, it has intermolecular hydrogen bonding. So due to which what happens, HF has highest boiling point and exists as liquid at room temperature. So the boiling point order is HCl, low boiling point, less than HBr, less than HI, less than HF. This is also very, very important. So from hydrates, you may expect a question because they are having different trends. They are having what? Different trends. That's why we can have this type of questions you'll get for the entrance exams, for the entrance exam. I hope it is clear. Let us see now. Next concept. Reactivity towards metals. Halogens readily react with metals to form their respective metal halides because metals has a tendency to lose electron and halogens has a tendency to gain electrons. And these metallic halides are ionic in nature. These metallic halides are ionic in nature because if you say sodium chloride, ionic in nature, sodium fluoride, ionic in nature, sodium bromide, ionic in nature, and sodium iodide also ionic in nature. So halogens react with metals to form respective metal halides. The ionic character of halides decreases from fluorides to iodides for a given metal ion. So within the sodium, so sodium fluoride is more ionic than sodium chloride, which is more ionic than sodium bromide, which is more ionic than sodium iodide. So sodium fluoride is more ionic. Why? Because the electronegativity value of fluorine is highest. So if the electronegativity difference between two combining metals is more, then it is more ionic in nature. I'm writing the statement electronegativity difference. If the electronegativity difference is high, then it is most ionic in nature. It is most ionic in nature. So automatically, if we take within the same element of fluorine, chlorine, bromine, or iodine with the same metal, we'll say the order of the metallic nature, the order of ionic form, sodium fluoride is more ionic. So it is most ionic. I hope it is clear. So metal halides with higher oxygen state are more covalent. Metal halides with higher oxygen state means like aluminum chloride is covalent in nature. Magnesium chloride, it is ionic in nature, but less ionic in nature than compared to first group metals. So SnCl4, PbCl4, Sn in plus 4 state, lead in plus 4 state are more covalent than SnCl2 that is plus 2 and plus 2 state. So this is called so metal halides with higher oxygen states are more covalent than metal halides with lower oxygen states. So if it is more ionic means more reducing nature. So they have more reducing nature when compared to this. I hope it is clear. So next, Oxides of group 17 elements. Halogen forms many oxides, but most of them are unstable. Halogens form many oxides, but most of them are unstable. Fluorine form two oxides, that is O2F2 and OF2. So OF2, the oxygen state of oxygen is +2, and O2F2, the oxygen state of oxygen is +1. Even though oxygen is non-metal, but it shows only positive oxygen state with only with fluorine, because fluorine is more electronegative than oxygen. That's why it shows positive oxygen state with respect to fluorine. This point already we have discussed in group 16 elements. Next, these are oxygen fluids rather than oxides due to higher electronegativity of fluorine. So these are called as oxygen fluids rather than oxides. And chlorine form oxides like Cl2O. The oxygen state of chlorine is +1 here. ClO2, oxygen state of chlorine is +4. Oxygen state of chlorine is +3. And oxygen state of chlorine is +7. So which are highly reactive oxidizing agents. These are the oxides of chlorine are most reactive. So these are called oxidizing agents because they readily oxidize the other elements and itself undergoing reduction. The bromine oxides like Br2O, BrO2, and BrO3 are least stable and exist only at low temperatures. I2O5 is a very good oxidizing agent. I2O5, diiodine pentoxide. The oxygen state of iodine is +5. So these are the oxides they form. So except fluorine, chlorine, bromine, and iodine can form more number of oxides due to availability of d electrons. Due to why they are forming many oxides due to availability of d electron due to availability of d electrons. Whereas in fluorine there is no availability of d electron. That's why it can form only two oxides. Rather than we'll call it they are not oxides, they are fluids. Because fluorine is more electronegative, that's why they are called as fluids. Whereas the for chlorine, bromine, and iodine, we'll call them as oxides. But with fluorine, we'll call it as fluids rather than oxides. I hope it is clear. Next, continuation. Now let us see which among halogens is the most abundant element. So the most abundant element is fluorine. The most abundant element is what? Fluorine. So I'll just go back. So next question. Why do the melting and boiling points of halogens increases in going down the group? Why the melting points and boiling points of halogens increases in going down the group? So as the melting points, so if you take the halogens down the group, what happens? Fluorine is a gas, bromine is a liquid, chlorine is a gas, and iodine is a solid. So automatically the melting points and boiling points of, so first, since fluorine is a gas, I'll write it here. Since fluorine is a gas and chlorine is also a gas at room temperature, but whereas bromine is liquid at room temperature and if iodine is solid. So first gas, liquid and solid. So automatically gas is having low melting points and low boiling points than liquid and solid. So the melting points and boiling points of halogens increases in going down the group. Increases in going down the group. I hope it is clear. Let us see next question. Considering the parameters such as bond dissociation enthalpy, electron gain enthalpy, and hydration enthalpy, compare the oxidizing power of fluorine and chlorine. So if we take the bond dissociation enthalpy, if we take bond dissociation enthalpy of fluorine and chlorine, fluorine is less than chlorine. Fluorine is less than chlorine. Next, electron gain enthalpy also. Electron gain enthalpy, which is easy to gain the electron. Fluorine is less than chlorine. Here, this also I write it clearly so that you can understand better. So, fluorine is less than chlorine. Next, we have hydration enthalpy. Hydration enthalpy, fluorine is greater than chlorine because fluorine is easily dissolvable in water when compared to chlorine. So fluorine is easily soluble in water when compared to chlorine gas. So that's why we can say these are the orders. So parameters such as bond dissociation enthalpy, electron gain enthalpy and hydration enthalpy. Compare the oxidizing power of fluorine and chlorine. So fluorine is less than chlorine. Fluorine is greater than less than chlorine in respect to electron gain enthalpy. And hydration enthalpy, fluorine is greater than chlorine. I hope it is clear. So these are the questions which we have discussed so far now. Let us discuss some more questions based on this. Just note it down in your classwork. All these questions are very important. I'm writing the question right now. Please note it down. Which among the following factors, writing the question here, please note down. So I'm clearing the diagram. Next. So since we have finished this, so I'll take like this. Which among the following factors, question number 4, which among the following factors, which among the following factors is the most important, is the most important in making fluorine, in making fluorine, in making fluorine the strongest oxidizing halogen, the strongest oxidizing halogen. So what makes it is the most strongest oxidizing halogen? Option 1, electron affinity, electron affinity. Option 2, bond dissociation energy, bond dissociation energy. Option 3, hydration enthalpy, hydration enthalpy. And option 4, ionization enthalpy. Option 4 is what? Ionization enthalpy. So here I'm writing, please note it down. Option 4, ionization enthalpy. So why fluorine is most strongest oxidizing agent? Because it can be easily dissociated, because the bond enthalpies of halogens follows order chlorine, bromine, then fluorine, then iodine. Since fluorine can easily be dissociated into fluorine atoms, so answer is bond dissociation enthalpy. So answer is second option, that is bond dissociation enthalpy. I hope it is clear. Next question. Next question. Question number 6. The correct order of thermal stability of hydrogen halides is the correct order of which is most stable. The correct order of thermal stability. Like these questions, they'll ask in the competitive exams based on general properties. The correct order of thermal stability of hydrogen halides. Hydrogen halides HX is HX, that is X is called halogen, is option A, hydrogen iodide greater than hydrogen bromide greater than hydrogen chloride greater than hydrogen fluoride. Second option, hydrogen fluoride greater than hydrogen chloride greater than hydrogen bromide greater than hydrogen iodide. Third option, writing it here, hydrogen chloride less than hydrogen fluoride, less than hydrogen bromide, less than hydrogen iodide. And fourth option finally, hydrogen iodide greater than hydrogen chloride, greater than hydrogen fluoride, greater than hydrogen bromide. So these are the four options we have. So let's just think about the answer. So what makes hydrogen? So the correct order of thermal stability, already we know hydrogen fluoride is more stable among the halides because it is having due to hydrogen bonding. Due to hydrogen bonding, hydrogen fluoride is the strongest, so it is very difficult to break the bond of hydrogen fluoride bond. So that's why the answer is hydrogen fluoride greater than hydrogen chloride, greater than hydrogen bromide, greater than hydrogen iodide. Why HF is having more thermal stability? Due to hydrogen bonding. Due to hydrogen bonding, it has more thermal stability. I hope it is clear. Now let us take question number 7. Question number 5 is finished. Now question number 6. Here itself I'm writing. So please try to understand. Next question. Next, the stability of dihalides. So dihalides, we are discussing about hydrogen halides. So in which of the following arrangements, this is mixed question, in which of the, and it's very important, in which of the following elements, arrangements, comma, the sequence is not strictly followed. The sequence is not strictly according to the property. Strictly according to the property. According to the property written against it. So you have to identify the incorrect combination. Incorrect combination. So first, let us see first option. Option A, carbon dioxide is less than silicon dioxide is less than tin dioxide less than PbO2. Increasing oxidizing power. Increasing the property is what? Increasing oxidizing power. Option 2, second option. Let us see second option. HF, that is hydrogen fluoride, less than HCl, less than HBr, less than HI. The property is what? Increasing acidic strength. Increasing acidic strength. So which is strongest acid? Hydrogen. So it is correct only. So it is increasing acidic strength. Next, third point. So as I told you, this is P block, complete P block elements. Ammonia less than phosphine, less than arsenic hydride, less than antimony hydride. Increasing basic strength. Increasing basic strength. And fourth point, that is option D. B less than C less than O less than N. The properties, sorry, here less than I forgot to write. So B less than, that is boron, less than carbon, less than oxygen, less than nitrogen. Increasing first ionization enthalpy. Increasing first ionization energy. So among these, which is the right option? Let us check now. So first one, as we know, carbon dioxide less than silicon dioxide, less than tin oxide, less than lead dioxide. So that is the properties increasing oxidizing power. So increasing oxidizing power, you have to check it now. Next we have, so this is increasing oxidizing power, it is the right answer. So hydrogen fluoride, hydrogen bromide, hydrogen anhydride, I already know it is increasing acidic strength. Increasing acidic strength is also correct. So the wrong one is ammonia less than phosphine, less than arsenic hydride, less than antimony hydride, increasing basic strength. So they are not having basic strength. So ammonia is more basic than phosphine, than arsenic hydride, than antimony hydride. So that's why this order is wrong. So answer is incorrect. Option is this. So incorrect option. Don't think it is tick miss. This is also right. So here it is not correct. So this is correct order only. This is also correct order, and this is also correct order. The incorrect means the incorrect statement is ammonia is more basic than phosphine, but it is given less basic than phosphine, arsenic hydride, and antimony hydride. So this is the answer. I hope it is clear. So this type of questions, inter-halogen compound means it is a inter chapters they'll ask definitely. Not only stick to one chapter only they'll ask. So that's why I want to discuss this. That's why I have discussed. I hope it's clear. Now let us see question number 7. 10 questions we'll do from this so that easily can understand more better. Which among the following is most reactive? Which, this question very important. Which among the following is most reactive? Which among the following is most reactive? Option 1, chlorine gas. Option 2, bromine gas. Option 3, bromine liquid they have given, maybe just element they have given, atom molecule. Option 3, iodine. And option 4, iodine chloride. This is interhalogen compound. So which is the right answer? Let us discuss now. So it is option 4 because it contains iodine as well as chlorine. So answer is fourth option. So interhalogen compounds are more reactive than halogens. Interhalogen compounds, by which you can write a statement. Interhalogen compounds are more reactive than halogens. Please note down this statement in your classwork. Next question, question number 8. Let us see question number 8 now. So question number 8, writing on the board. Please note it down. Which of the following halogen? Which of the following halogen? Seventh question is most important. Eighth question is also important. Which of the following halogen? Which of the following halogen disproportionates in water? Undergoes disproportionation reaction. Disproportionates. This is easy. Disproportionates in water. What is disproportionate means? Simultaneously same element undergoing oxidation as well as reduction. Disproportionate in water. So straight away we can say answer easily. So option 1, what they are given here, fluorine, chlorine, bromine, and iodine. So option B, chlorine. Option C, iodine. And option D, most interesting, all the three. And we already know fluorine cannot disproportionate because always its oxygen state is -1. So it cannot disproportionate. Only it can go oxidation or reduction. So chlorine is the disproportionate because chlorine undergoes disproportionation reaction. So answer is B. Answer is what? B. We can see disproportionate reaction of chlorine. So you can see disproportionation reactions examples in stoichiometry, which is in 11th class. I hope it is clear. So chlorine is the halogen which can disproportionate in water. Next question. Which of the following is correct statement? So this I have to clear the time. So because it is a lengthy question. So I'm clearing the drawing. Now question number 9, writing it again separately. Very, very important. Which of the following is correct statement? Which of the following, which of the following is correct statement? So these are the questions based on general properties. So that's why I want to discuss question, because in these questions are most important. F2 has higher bond dissociation energy than fluorine. Bond dissociation energy than Cl2. What is BDE? Bond dissociation energy. Bond dissociation enthalpy. Next, option B. Fluorine has higher electron affinity than chlorine. Higher electron affinity than Cl. Third option. HF is stronger acid than HCl. HF is stronger acid than HCl. So all based on general properties only. So they can ask statement based question like this. So all the general properties are very important. And fourth one, boiling point increases down the group in halogens. Increases down the group in halogens. So what is the correct statement now? So fluorine has higher electron affinity than chlorine. This is wrong. HF is stronger acid than HCl because down the group hydrogen iodide is strongly acidic than hydrogen fluoride. Boiling point increases down the group in halogens. So the right answer is, let us see the right answer now. Just think about the right answer in your classwork. So first statement, fluorine is having higher bond enthalpy than than so first statement, F2 has higher bond dissociation enthalpy than chlorine. F has higher electron. These two are wrong statement. HF is stronger acid than HCl because hydrogen fluoride is more electronegative due to hydrogen bonding. So it is stronger acidic than HCl. And boiling point increases down the group in halogens. It is correct. So it is a wrong option. So correct statement is only HF is stronger acid than HCl. HF is stronger acid than HCl. So answer is third option. I hope it is clear. Next question, 10th question we are discussing. Based on general properties only, I'm discussing the questions. So please note it down. All the important models I'm discussing now. Last question, able to find. So, question number 10. Among the halogens, which is stronger oxidizing agent? Oxidizing agent. Option A, fluorine. Option B, fluorine. Option C, bromine. And option D, iodine. So it is undoubtedly this fluorine. So among halogens, stronger oxidizing agent is fluorine. So I hope it is clear. So This is the question. These are the questions based on general properties. Still more questions you can work out from competitive books. Easily you can understand. I hope it is clear. So this class I'm just after general properties. This class I'm just going to end now. So please go to all the slides easily. Easily you can understand because this is only theory topic. I hope it is clear, and do more questions based on competitive exams from this chapter. Thank you.